Today we're going to talk about section 14.4 that covers the topic of arc length, length along a curve. Now you have seen this topic before in a portion of the class, probably in Calc 2, but it was in the case of y equals a function of x, and then depending on your professor you may have seen it in the parametric form. So let's just say previously it looked something like this. You have some function, the graph is y equals f of x, and you're working between some point A and B on the x-axis. Why did I draw one as a point and the other? I don't know what's going on with it. Let's make them both points. So there's a section of this curve that lies above those points, and the arc length measured along that curve, it was given by an integral. It's the integral of the square root of 1 plus f prime of x squared dx. And that's with the x variable running from a to b. So it's a definite integral. Get your actual length. How do you physically interpret that? I have here a tool that I bought back in my days of engineering work. This is a ruler. It's got markings on it, but it's also flexible. And I think it's a great way to illustrate what happens to measure length along a curve. You find which end is 0. Here it is. And you stick the 0 marking along there, and then you bend this ruler until it fits the shape of the curve pretty well. And curve I wrote there was about 6 1/4 inches long. That's the physical process we're trying to get at. In other settings, I think people who do sewing, for instance, will have recognized these tape measures that are very flexible, sort of ribbon-like. You can measure yourself with those kind of things. You know, at worst case scenario, you can take a piece of string and lay it out along the curve, cut it off, and then measure the length of it once you straighten that string out. But this arc length, however you manage to measure it or compute it, is usually called S. Another version of this was the setting when y was a function of x, but another version is sometimes looked at in Calc 2, and this is where x and y are both functions of time. So you have a curve that's given parametrically, and in that case you may not have a function. The position vector looks like let's see, f of t comma g of t. Well, they wouldn't have called it a position vector back then when you were talking about this in Calc 2, but that's how we refer to it now. And in this scenario, the integrand changes a little bit. You still basically integrate from a to b, but now, look, a and b don't represent places on the x-axis, they represent time values. So maybe here's t equals to a. Halfway through the loop-de-loop is t equals to b. We get the integral of the area, the length of this portion measured along the curve. I'm going to try to make it look bold so we see it. Again, by doing an integral. This s would be integral from a to b. In a way, it's simpler because the form is symmetrical. Here there's a difference between the x-axis and the y-axis. Here both x and y are the same in that your values on those directions are determined by the variable t. So what you need to do is figure out the derivative of that thing and take its length. This is the square root of the sum of the squares of the components. And of course that integral is done with respect to time. So when we go to do this in 3 dimensions, that's the one we model. It's that in 3D the integral is just going to have an x, y, and a z coordinate function. So the arc length S for a 3D curve just looks like this. Square root of, what are we using? F, G, and H, I think, for our coordinate functions. So f prime of t squared plus g prime of t squared plus h prime of t squared, integrating with respect to time. Why is this the thing to do? I just sort of want to motivate for you why we actually do that. And the best way to think of this is to refer back to Riemann sums. Imagine this is actually in 3 dimensions. We've got some funky curve like that, and I'm trying to measure the length from t equals a to, how about down here, t equals b. Well, what I could do is divide the interval from a to b on the time coordinate up into a bunch of bits. Here's the halfway point. Here's a quarter of the way there, and there's a quarter of the way there. That's probably no, that's going to miss the loop-de-loop. So here, I've split this thing up now into 8 little sub-chunks. And what you could do is do straight line distance in between each of these things. That's kind of weird. It lost the loop-de-loop character, but it still has close to the same arc length. Maybe this is where it's the worst. The rest of the graph, actually, it looks like the arc length along the straight lines and the arc length along the curve are fairly close to one another. Maybe we should have thrown in an extra point in there to make it better. But adding up all of those, that's just a Riemann sum. If we make the division finer, let me see if I can do this for you, for at least a portion of it. Suppose we cut each one of these intervals in half. Now I could make a red curve, also made out of linear bits, piecewise linear curve, that, whoops, went to the wrong one. I'm going to follow the piece of the curve I'm on. That would look like this. And it's already clear that, whoops, I'm missing some parts. Yeah, I just went past a point that I was supposed to hit. Okay. Yep. That's already closer to the value. If we halved everything again, we'd get a... So how does that process really work? This integral is the limiting value as some parameter, let's call it n for the number of subintervals, as n goes to infinity, of a sum. And the sum is going to be, well, it's going to be the length of a line segment that goes between 2 points. Let me just say segment in here. For us, we don't really need to care too much about the details of this Riemann sum. We just want to think about broadly about this. The integral we're after as the limit of a Riemann sum. I guess maybe I should at least do the segment's length. So I just want to concentrate on what would one of the segment's lengths be, especially if we were close to infinity, n was really, really large. Well, that sort of corresponds to we've zoomed way in on the graph and we're getting a straight line that's very, very close to being the actual path of the graph. So how about we do that like right around there, right? Where I've just drawn a circle around, think of that as the magnifying glass. And now we're going to look at that blown up, a much bigger view of it. So here's the magnified view of that little region right there. The curve is coming in sort of like this and going back out the top. And then we're going to have, we had that point right at the bottom. Here's another point along the curve, just a little bit down. This is happening at t, and we'll call this one at t plus h. I want to be smarter about what I use for the variable because remember how we used f, g, and h as the coordinate things? Let's call it delta t. T plus a small change in t. Well, how long is that line segment? Because that's the thing that we're trying to do the sum of. And it's actually pretty easy because this curve is given parametrically by the position vector is this guy, f of t, g of t, h of t. And what we're really doing when we go to the limit is we're thinking about this, I've drawn it as a secant, but what we really want to think of it as a tangent. At time equal to this t here, we're having this tangent who has a certain length. In fact, the time length of it, the duration over while the point moves from t to t plus delta t, is in fact delta t. But what direction does it move in? What's its vector quantity? It's a tangent line to the curve, so it's the velocity vector. Velocity of t. It's the thing moving in the direction of the curve, in the positive orientation. So it should start with a brace. It's brace f prime of t, comma g prime of t, and h prime of t. I think I can take away the original drawing and we're just looking at the blown up version of it now. A very close approximator for this, and because this is actually what we get in the limit, but the thing that's a very close approximator to it, let's call it, how about u, since u is another vector, but it's similar to v. So let me say that v is approximately equal to u. And what u looks like is a change in f over a change in time, a discrete change in f, delta f over delta t, and delta g over delta t. And same thing, delta h over delta t. So how long is this u? And as we let delta t get smaller and smaller, the u literally turns into the v. Well, its length is sort of interesting because it depends on what delta t is. This thing's a velocity vector, and I guess we need to think for a second about how do you get distance traveled if you know what velocity is. If I know I'm going 60 miles an hour and 2 hours have elapsed while I took some drive, how far have I gone? 120 miles, right? Does that example make you think, okay, we should multiply? That is, the distance is equal to your speed. Gosh, I'll just write it out. Speed times time. Problem is we used s previously as well. This can be seen in a bunch of different ways. Speed equals distance divided by time, and there's probably one more way to do it. Time is distance divided by speed, sure. Anyway, that's the fundamental relationship between distance, speed, and time. So the speed that we're going is how long is this vector. I'm going to do it in the approximating case, the length of vector u. The time is delta t. So the thing that we're thinking of as a little increment of the distance is the length of the vector I've just written down there. Let's call it just the length of u for now, times delta t. Right. So let's work out what is the length of vector u. Its components are right in front of us. Right. So we just square root the sum of the squares, and this is why the formula comes out the way it does. What we get here is the square root of delta f over delta t, delta. Yeah, no, that's right. Delta f over delta t squared plus delta g over delta t squared plus delta h over delta t squared. And that's all under the square root. And then outside of the square root, we've got a times delta t. Well, if we go to the limit, there's some funny business that you got to see here. You notice how the squaring is going to make delta t in the bottom of each one of these fractions? So all those fractions could be combined into one, and it would have delta t squared downstairs. But we're under a square root, right? So these delta t's down here really contribute a 1 over delta t to the whole thing. And there's a delta t out here. In other words, this thing can simplify rather a lot. The change in distance, the little deltas that will add up to get the actual distance, is square root of delta f squared plus delta g squared plus delta t squared. I'm sorry, h, fgh squared. Because the over dt's in here are going to cancel with the times by dt, delta t there. Yeah. Well, that's the thing that we move to the limit in, and we get that this is approximated rather closely by the square root of the derivatives, f prime at t squared, g prime at t squared, and h prime at t squared. Of course, in this form, I have reintroduced those dividing by, well, now it's dt. Okay, one more thing to do, I guess, to show you. This is exactly equal to, change these to Leibniz notation. That one is df dt squared. This one is dg dt squared, and the other one is dh dt squared. And so maybe you see it now. This is really the same as what was down here. The deltas have turned into d's, but this is moving to the limit where the delta t is actually vanishingly small. And we do need the dt on the end here. Well, that, which is approximately the same thing as this, well, no, sorry, which is equal to this, but it's approximately the same thing as our Riemann sum integrand thing. I mean, I'm trying to provide evidence, at least, that this is the right thing to do. That by integrating the sum of the squares of the derivatives components with respect to t, you'll get a little chunk of arc length. And the heuristic you should keep in mind is that when you're integrating, you're just adding up so much. You're adding up infinitely many tiny, tiny chunks, adding up infinitely many zeros until you get the actual thing. Well, that's sort of the zen of it. I don't know that it's a good way to describe it right now, but you know, we'll live with that, I suppose. Okay, so can we put this to some use? In the book, they do a couple of things. I didn't like either of their examples, so I came up with another one. What I want to look at is a helix, or a spiral curve, in three-dimensional space. So I wanted to start on the x-axis and go around one loop of this helix and winding up above that same point on the x-axis. So it's a spiral. It looks like it's going straight up there, but it's actually going away from us there. And the curve, the formula for this particular helix, a parametric version in terms of time, is the following. It's 4 cos t. I put particular constants in here to make it come out nice. 4 sine t and 3t, right? Yeah, 3t. So it's actually probably a bit steeper than I know. The z coordinate is going up quickly. You can see what's going on in the xy plane. That's the parametric form for a circle. And so it's describing a circle in the xy direction, but it's ascending in the z direction proportionate to t. Actually, 3 times what t is. So that's why it's rather steep. It's more like this. Let's see, we can think about how steep it is, I suppose. We go around one loop of this circle as time goes from 0 to 2 pi, about 6. In the vertical direction, as we move, it's a little more than 6. We're going to, as t goes through a range of 6, this is going to go through a range of about 18. So while we're going through this circle whose radius is 4, the radius is 4, we're also going vertically 18 units. That's kind of a lot. Although, wait, I don't know. We could plot it on Sage if you want to see exactly where it is, but the numbers are actually chosen. You might recognize those numbers because of the 3, 4, 5 triangle. We're going to get a nice round number out of this when we integrate. All right, so let's go to it. According to the formula that I've at least tried to justify just now, we should get the arc length along this one branch. It's called S. People always use S for arc length. It's the integral from, in this case, it's 0 to 2 pi. The time parameter needs to go from, when you're at t equals 0, then 4 units out on the x-axis and 0 units out on the y-axis, so right there. And when you get to 2 pi, you've gone completely around the circle. So that's the time interval we want. So we have to integrate the square root of the sum of the squares of the derivatives here. Okay, before I go back up to the top, let's figure out what the velocity vector is. The derivatives of these guys. Cosine goes to minus sine, so we get negative 4 sine t. Sine goes to cosine, so the constant comes along, 4 cos t, and that becomes a 3. So that's our f prime, our g prime, and our h prime. I can write it down then. We want the square root of minus 4 sine t squared plus 4 cos t squared make that a little longer, plus, what's the last one? 3 squared. Yep, and that's excellent because what do we have? 16 sine squared. Let's go ahead and write it up. 0 to 2 pi square root of 16 sine squared t plus 16 cos squared t plus 9. And I hope everybody recognizes this identity, sine squared plus cos squared equaling 1. So this this long bit of junk right here is actually just a 16. So you have the integral from 0. Oh, darn, I just recognized something bad I did. When you integrate, you always have to end with a d something or other. These are integrals with respect to time. So that should be dt there. And square root of 25, that's 5 dt. So I forgot the upper limit too. Integral 0 to 2 pi of 5 dt. Well, that integral certainly is doable, right? We get 5t evaluated between 0 and 2 pi. Brain failure there. Okay, so that's going to be 10 pi minus 0. Just write that there. 10 pi. But a little over 30 units, 31.4 something units, whatever the units of this are, I didn't say. All right, so you can do it sometimes. But I will tell you, just being honest, most of the times when you try to do an arc length integral, it is going to fail. Unless they have cooked it up very specifically. There's about 3 curves where we can actually compute the arc length along them. Most of the time this doesn't work out. Well, what do you do? When you've got an integral, you know the integral's value would get you this physical constant you're interested in, but you can't, there's no closed form solution for that integral. Because that's what we have to do most of the time. Well, the way I put it here, arc length integrals rarely work. Usually we evaluate numerically. Yeah. Most of the time, there's no closed form solution to an arc length integral. What are you going to do in that setting? Use numerics. Add things up by doing the Riemann sum I was alluding to before, and see what you can get. Oops. I just changed pens hoping to get a darker one, and it came out lighter still. Let's try this. Oh, that's good. So we integrate numerically. Despite this fact, knowing that there is a way to compute arc length along the curve, even if it means we have to go to a computer to get the answer out of it, is theoretically useful. Right, we're going to create a function using that arc length integral. Usually it's called S of t. So it depends on t. You should have the picture like this in mind. There's some curve that we're following. Here's maybe where t is equal to 0. But we want to measure along this curve from some particular starting point, A, to some particular value down the line, t. Okay. So S of t would be how far we've traveled from our initial point until we arrive at time t. And I don't know what we do with, I guess if time is prior to A, if the t we're interested in was back here, I suppose the arc length would come out negative. I have to think about that. It's probably that, yeah, because the endpoints would be in the wrong order, so you'd have to switch the endpoints, and that throws in a minus sign. Anyway, let's just visually think about it as t is some point later in time than A was, the starting point. So what is S of t? It's the integral from A to t. And you recall the function I just wrote. It was a square root of something where each thing was a function of time. But now I'm using time as the upper limit. So I have to be slightly more honest about things. Let's call this axis that we're using, the t-axis, is actually, how about u? This is u equal to 0. And this one is u equal to a. And this guy, I still want to say it the other way, is u equal to t. In other words, this integral happens for u values, switching from a, moving slowly up to t. Or slowly isn't material, continuously. All right, so that is the derivatives of our function need to be written in terms of this new parameter. It's just a placeholder. It might as well have been t, except I wanted to use t for the time variable there. All right, so what is it? It's square root of f prime at u squared plus g prime at u squared plus h prime of u squared. I finally made the square root longer than it needed to be. du. U is really only thrown in there to give us a different variable to do the integration with respect to. We're really figuring out how long is the curve between A and the point T. It might help us to see this as a vector equation. You see that square root of the sum of the squares? That's just the length of the velocity vector. So you could also write this as the integral from A to T of the length of, excuse me, of the velocity vector. that length changing with time, which we're calling u for right now, d. And I guess this is probably my favorite version of the formula that we're doing here, because s is supposed to be the length that we travel, the distance that we travel along the curve. What is this? We're adding up speed, the length of velocity, times an increment of time. Speed times time is distance. So we get distance as the output of it. There's an approach to calculus which I rather like. It says the following: if you want to calculate any particular thing, if you want to calculate work, figure out what differential work is, and then integrate. If you want to calculate, energy, determine what differential energy is. The integral of differential energy will be energy. We're trying to figure out arc length. We should be integrating differential arc length. And that's what this is actually about. This is a tiny little piece of the curve, which corresponds to an infinitesimal change in the time coordinate, multiplied by the speed of the point in motion at that time. So I just erased and recopied the result that I had at the bottom of the board up at the top. The reason I did so is I want you to use the fundamental, I'm going to do it, but I want you to think about using the fundamental theorem of calculus here. What we've got there is an integral where the variable is actually in the upper limit. If I take the time derivative of both sides of this, on the one hand I get ds dt. That is actually a function of time, but people normally don't write the of t after it. Is it wrong of me to write it? I'm gonna leave it anyway. The other side, it's a little harder to think. What do you do to take the derivative with respect to time of something that looks like this? With time is the upper limit. And the fundamental theorem of calculus actually has an answer to that. If you're taking the derivative of an integral, it's just look at the integrand. You have to, one way to think of this is the area under a curve, except that you're thinking about, okay, here's the curve, you're getting the area from A up to some point T, but T is moving, right? You're going to increase T. So how much does this area change if I bump T up a little bit? Because what we want to do is figure out the rate of change of this area. If I'm changing the time just like 1 second later, the amount of area changes basically is the area, basically if the width of this is 1 second, then just the height of the thing gives you that area. So that's the idea. If you're taking a time derivative of something with t in the upper limit, you just get the integrand. That is one of the variants of the fundamental theorem, so I'll just leave you to see that, or maybe look that back up. But ds dt is equal to the length of the velocity vector. Except I need to evaluate, don't I? I was taking a derivative. Yeah, I think I am supposed to evaluate at a and at t. All right. How far have we gone if we're still at our starting point? That's what A is. Yeah, you haven't traveled at all. So the value of this thing at 0 is 0. And the value at t is the length of the vector v of t. I feel a little wonky about that, but the arc length at A is by definition T. A was our initial point. Okay. Right. I guess I'm okay with this. I better be, because look what it literally says. I mean, what is dSdt? That's the rate of change, the time rate of change of our position along the curve. It's how far we've drawn, it's the derivative of how far we've gone along the curve. And what is this? The length of the velocity vector. Well, this one is speed, because the length of velocity is certainly speed. Do you see that that one's also speed? It's how fast the curve is, the point in motion is moving at any particular time t. So since they actually are the same thing, it makes sense that we've set them equal to one another via some calculus magic. Finally, we're going to talk about a really important idea. Using this arc length function, despite the fact that we may never be able to calculate it, but that it theoretically exists, there certainly is some relationship between how far we've traveled and how much time has elapsed. Using the arc length formula as a theoretical tool. And you have already seen this once in your lives, at least. What we're doing is, what we want to talk about next is a parameterization by arc length. Here's the place where you've seen this previously. If you think about motion along the unit circle, that was a terrible circle, but it'll do. The point in motion is, its coordinates are given by the cosine and the sine function. Cos of t, sine of t. That's a circle of radius 1. Right? How far do we travel in going around a circle of radius 1? A very egg-like circle of radius 1. We go 2 pi units. And in fact, that's the arc length around this circle. That t in there, I mean, you know, a lot of times I probably should have called it theta right now because you're supposed to think about angles, but I accidentally called it t. Because what is it really? It's how far around the arc we've traveled. That is, t in this case is literally equal to s, the distance traveled. If you've gone 1 unit of distance, 1, how far around that circle have you traveled? This is the definition of what a radian is. This amount of arc length, as we travel 1 unit around the circle, that's theta equals 1 radian. And whether you think of it happening in there, or you think about it happening as arc length out there, that's just your attitude to it. The point is, that t is the same thing as arc length. Now, I hope you become convinced at this point that using radian measure is actually good, because degrees are a weird, messed up unit that, you know, comes from ancient Babylon. We don't really need those. For scientific stuff, radian measure is the thing to use. And why is that? Why should we want to have things that are parameterized by arc length? Well, if you don't use arc length as a parameter, then the way you calculate things about your curve depends on the parameterization. And I don't want to have, you know, if I'm trying to think about things like, you know, for instance, I might want to say, how curved is this curve? What's the radius that it's bending at? This is something we can compute. But if I have it parameterized by time, I could have it parameterized by time multiple different ways. Each of them would give me a different answer. When I standardize and say, let's just imagine we're walking along a curve at 1 unit per time unit, then we've got an arc length parameterization. What was I starting to write here? If you use something other than arc length, well then the computations you do about the curve are going to depend on what that something other is. You don't want to use a time parameter. I could follow the same path in multiple different ways with different profiles of how fast I was moving at different times. So if I'm looking to get just the geometric character of that path, arc length is the thing to do. And here's where the function that we talked about, the arc length function, comes in. Well, let me finish this sentence. The values we compute will depend on the parameterization. But if you make arc length be the parameter, it'll be really nice. Things will come out smoothly, or they won't depend on the parameter anyway. One way to think about this, if you're moving along the curve and you still want to think about it in terms of time, think of moving at unit speed. So, depending on what you're using for units, unit speed can be very, very different things, but nevertheless, think of moving at unit speed, and you'll be doing the same thing as doing an arc length parameterization. I was going to mention some of the different possibilities for having speed 1. If I'm thinking about walking 1 mile an hour, that just means I have to slow down really. I mean, most people's normal pace is about 3 miles an hour. So if you just really dog it and walk really slowly, you're going at speed 1. If, on the other hand, I measure things in 1 meter per second, that's kind of quick, right? A meter is like this long. Can I go through that distance in a second? I don't think I can run that fast. Anyway, that's a fairly big speed. If I measure things in terms of the speed of light, then one meaning the speed of light, is really fast. Whereas, so there's other things. Like, for instance, geology people measure the speed that the continents are drifting around on the surface of the Earth. They're something in the order of inches per century is what you measure. So speed 1 there would be 1 inch per century. Not a lot of motion, but it's actually detectable. Those guys have figured out how to do that sort of stuff. All right, so well, what do we want to do? We usually have a parameter that's time, or best thought of as time, and we can't actually compute the arc length, but we know there is this relationship. So you know that S is a function of time. S of t exists. You might prefer to not write it this way, but to write it as S is some function of time. S equals f of t. But what if you want to go from t to s? What are you doing? I mean, really, I guess I want to write a function that looks like this. Time as a function of how far along the curve are we? And that exists too. So if you can see it maybe in this form better. What if I wanted to have t equals something of s? I've left a blank there. What goes in there? That's the inverse function, isn't it? That's f inverse of s. So, missing a parenthesis. So if you want to get this t of s, that's exactly what it is. You find the inverse relation. Now look, if the s of t exists, it'll have an inverse. At least locally, it'll have an inverse. It's conceivable, I suppose, that the inverse thing might not be a function. There's times when that happens. I can't think of one off the bat. It feels like that should always be a function. But anyway, it's a possibility. But if you're looking at a small region, you can always isolate to the point where you do get a function. So my notes have just ended. I didn't go past this point in the notes. Maybe this is where we were meant to stop.